Okay, now let's get to work. Let's start our first chapter, relativity. In fact, we're going to mostly deal with the special theory of relativity. Let's begin with classical physics, with the name of Galileo Galilei. And we start with what's called Galilean relativity. You know, Newton's second law, along with any other law of classical mechanics, is not valid only in one reference frame, is it? Of course, we have to have an inertial frame, right? The frame cannot accelerate, otherwise F is not equal to ma anymore. We have to use what's called pseudo-force and so on. But let's say we're looking at an inertial frame. Newton's second law is not only valid in one inertial frame, it is valid for all inertial frames. So let's consider two reference frames, S and S prime. They're both inertial, which means they're not accelerating. At t equal to 0, the two frames, S and S prime, are exactly coincidental. They're in the same location, at the same location. Okay, but the difference is S prime moves relative to S with a constant velocity of v along the x-axis. Okay, so starting from t equal to 0, where they are at the same location, S stays where it is, but S prime starts to move away from it along the x-axis. So after a time t, it must have moved a distance of v times t from the origin of the S prime, of the S reference frame, right? And therefore, if you look at a certain point, okay, or point P, right, and you say, I want to find its coordinate. Well, since S prime does not move relative to S in the y direction or in a z direction, you can bet that when you measure this point, okay, measure its coordinate in the y and z direction, you're not going to get any difference whether you use S or S prime as a reference. So in other words, y prime equals y, z prime equals z, okay? Again, y prime is its coordinate, its y coordinate measured in S prime frame for this particle P, okay? What about x? Well, you can see here, this is from here to there, by definition, okay, measured from the origin of the S coordinate frame. This is x, okay, the x coordinate from here to there. But in S prime frame, we have to measure from there, so from here to there, that's x prime, right? So clearly, x is longer than x prime. No, I'm sorry, this is x prime. The difference is vt, isn't it? So therefore, x prime equals x minus vt. Okay, we have those kind of knowledge before. I just want to confirm with you. What about t prime? T prime is the time measured in S prime frame, and t is the time measured in S frame. Of course, if you have a good clock, which is mechanically accurate in both frames, then there is no reason why the time would be different. In other words, both reference frames will agree on the same time. It goes almost without saying that t prime equals t, right? Okay, so this combination is called Galileo transformation, which takes you from one inertial frame to another inertial frame. Okay, and we can look at classical mechanics in these two frames. Classical mechanics in the S frame and S prime frame. Okay, at the heart of classical mechanics is Newton's second law, which is F equals ma. I can write F equals ma as F equals m times the second derivative of coordinate. Okay, of course, you can also look at y and z, but this is only the x direction. The y and z direction are even easier because y and y prime the same, z and z prime the same. So if you look at only the x direction, so this is f of x, okay? That's the second derivative of x. Now, we can easily find that Newton's second law is valid in both reference frames because assume that fx prime equals fx, or the force is the same no matter who's measuring it, right? The mass is the same, m prime equals m. All these things go without saying. There is a difference between x and x prime, but we're not going to be too concerned about that because x prime is equal to x minus vt, as you know. And if you take a derivative, okay, you take a derivative, the first derivative, you're going to get dx prime dt equals dx dt minus, what is it? Well, v is a constant, okay? The reference frame S prime moves at a constant velocity relative to S. So V does not change. So it's a constant, and then that's it. Now, if you take one more derivative, you can get acceleration, right? So second derivative, okay? And that's the second derivative here. And dv dt is 0 because V doesn't change. So you see here, the accelerations are the same, even though the velocities may be different. The acceleration is the same. Okay, and the force is the same, mass is the same, the acceleration is the same. Therefore, if Newton's second law is valid in one reference frame, S, I can write the same thing. Fx prime equals m prime d squared x prime dt prime squared. Okay, t and t prime the same anyways. So you see, Newton's second law is not very choosy about which reference frame you apply to it, as long as it is inertial frame of reference. Okay, this is summarized in the so-called principle of Galilean relativity. What does it say? It says that Newton's second law, and with that, all other laws of classical physics, of classical mechanics, I should say, all laws of mechanics, as long as we restrict ourselves to mechanics, are valid in all inertial frame of reference. Okay? As long as the frames are inertial. So in other words, if you try to do an experiment, a mechanical experiment, okay, you are not going to be able to determine which reference frame you're in, because all reference frames will yield the same result, F equals ma. It's governed by the same law, F equals ma. This is why, if you are on a smooth sailing cruise ship, okay, there's no vibration, no acceleration, whatever, it's just smooth sailing. And if you lock yourself up in a windowless cabin, okay, would you know that you're moving? You probably wouldn't. And unless the thing vibrates and the thing rocks and you're seasick, but that is because it's accelerating. Okay, but suppose it doesn't accelerate at all, you cannot tell you're moving. And if you try to do an experiment, let's say you throw a ball to the ceiling and catch it later, you roll a ball down the incline, whatever you do, anything that you do mechanically, and you try to make your measurements, you will get exactly the same result as another person performing the same experiment on a land-based laboratory. You cannot tell at all that you're moving, nor can you tell how fast you're moving, okay, relative to the land-based laboratory. In other words, the cruise ship and the land, they're equally good in terms of applying Newton's second law. Okay, this is an example of Galilean relativity. But the Galilean relativity is restricted to mechanics. Okay? But we have more knowledge in physics other than mechanics. What if I want to do a different type of experiment? What if I play with a beam of light? I want to do an experiment about electricity and magnetism. Of course, light is included. What's going to happen? Will I be able to tell that I'm actually moving relative to the land-based laboratory? In other words, does Galilean relativity extend beyond classical mechanics? Okay, so to do that, we have to write down the equations that replace Newton's second law, and that is the Maxwell's equations. Okay, that's the equation set that governs the behavior of the electromagnetic world, right? So we have a set of equations, Maxwell's equations. I wrote it in a differential form. You can also write it down in integral form. It's the same thing. The importance here is not because I have 4 equations instead of one. The major distinction here between Maxwell's equations and Newton's second law is that I have now 2 constants. There's epsilon naught, which appears in everything electrical, and there's mu naught that applies to everything magnetic. Okay, I have a pair of fundamental constants. Unlike Newton's second law, which doesn't have any constant in it. And we can simplify this equation set if we look at vacuum where there's no particles, so density of charge equal to 0. And of course, there is no motion of charges because there's no charge in the first place, so J equal to 0 as well. We can rewrite Maxwell's equations like this. Gradient dot E equals to 0. Gradient dot B equal to 0. First and third equation. That basically means these two fields, E and B, are without divergence, so they are purely rotational transverse fields. Okay? And then you have gradient cross E equals negative partial B partial T, and gradient cross B equals epsilon naught partial E partial T. Now, if we focus on the next two equations, these two equations, we can easily eliminate either E or B. Okay, for example, if we take this E here, I want to eliminate B. How do I do that? I notice that gradient cross B equals something, a function of E. So I can take gradient cross on both sides. So I get gradient cross E. Okay, and that equals to negative partial T of gradient cross B, right? I just take gradient cross on both sides. But this gradient cross B can be replaced with epsilon naught partial E partial T. So this is epsilon naught negative partial T, epsilon naught partial E partial T. But that side, gradient cross E, there is a formula in calculus, which I'm sure you have learned. Okay, you may not remember it, but you have certainly learned that. There is an identity. This is gradient dot E minus gradient squared E. Okay? Trust me, that works. And this is 0. You can see this is 0, so we cross that out. Take the two negative signs, cancel each other, take the epsilon out. And so what do we have here? We have as a matter of fact, you know, I made a mistake. Sorry, there's a mu naught here. Here, and there is a mu naught here. There is a mu naught here. Okay? This equals to epsilon naught mu naught times the second derivative of E with respect to time. And if you compare this with the standard wave equation, which says in a three-dimensional space, gradient squared of any function of that behaves like a wave, we call it function psi, equals 1 over v squared times the second derivative of the same function with respect to time, that v being the speed of that wave. If you compare these two, then we find a vector wave, okay, which is the electric field, E, behaves like a wave. And actually, B behaves like a wave too. And the speed of that wave, epsilon naught mu naught, equals 1 over v squared. Okay, now this v is different from any other speed we have learned in classical physics because it is determined by a pair of fundamental constants. These constants has nothing to do with what kind of material it is, okay? It's not we're in water or we're in air, whatever. These are in vacuum, okay? There is no dependency on specific materials. These are universal constants. And we equate 1 over v squared with epsilon naught mu naught. And since that v is a constant, we call it c. C standing for constant. And we get the speed of light in vacuum. This, of course, is a review. You know that stuff, right? From Physics 1C. And when you plug in epsilon naught mu naught value, you get 300 million meters per second. This is, of course, one of the greatest success stories of classical physics. Maxwell derived the electromagnetic wave, as we just did before, and he found the speed of light to be the same as the speed of electromagnetic wave, so that convinces him that light was a form of electromagnetic wave. Okay, so that's just really great. But if you think a little bit deeper about this, you know, again, this speed is unlike any other speed. It's not like the speed of sound in water and the speed of sound in air, which is different, and so on. This speed depends on a pair of fundamental constants, so it itself is also a fundamental constant. But we know, on the other hand, according to Galileo relativity, speeds are not independent of reference frames. Okay, different reference frames measuring the speed will get a different result. For example, if you see a car zipping by at 60 miles per hour, to the passenger in the car is not moving at all, right? So therefore, you and the passenger in two different reference frames will yield different values for the speed of the car. But what about the speed of light? The speed of light is equal to this. It seems to be a constant on the one hand, but on the other hand, all speeds, according to Galileo, should depend on the reference frame. So the question is, in which reference frame are you going to get that speed? And if you do get that speed in one inertial frame, aren't you going to get different values in another reference frame? Remember, this is the speed of light. It's also the speed of any electromagnetic wave in vacuum. Does that mean that if you are locked up in that, cruise ship cabin, you will not find how fast you're moving or you're moving at all if you're doing mechanical experiment? What if you measure the speed of light? Okay, you measure the speed of light. Is it possible that you're going to find a different result than this? Because after all, you're in a reference frame that is moving relative to the Earth frame, right? And if that happens, then can't you use that difference in the speed of light that you measure to deduce how fast you're moving? In other words, now it looks like absolute motion does exist. Everybody can simply measure the speed of light, come with a slightly different value than this and say, okay, I know how fast I'm moving, relative to a certain special frame in which the speed of light is exactly equal to 1 over square root of epsilon naught mu naught. This is striking. It tells us that the two things that we took for granted before, one is Galileo relativity, has actually, and the Maxwell's equation, they're actually conflicting with each other. Okay, this means that Maxwell's equations, unlike Newton's second law, are valid only in one specific reference frame. If you go to a different reference frame, you're going to change the speed of light. Okay, so the laws of mechanics are valid in all reference frames, inertial reference frames, but you cannot say the same thing for the laws of E and M, because for one thing, the speed of light values will be different in different reference frames. That's according to Galileo relativity. So what do? How do we resolve this internal conflict with two different branches of classical physics? One is classical mechanics, the other is E and M. Well, scientists have learned that after Maxwell discovered the Maxwell's equations and prior to the introduction of relativity, and they had a lot of debate about what to do. Okay, it looks like there are two ways out. One of them is to say, all right, the principle of Galilean relativity, which states that all laws of mechanics must be the same in all reference inertial frames, this cannot be extended beyond mechanics to E and M. Okay, it is only valid for E and M. I'm sorry, only valid for classical mechanics, but not for E and M. And when it comes to E and M, electromagnetic phenomena, there exists a preferred frame of reference. Okay, for light. Even only in that frame, is the speed of light equal to 1 over the square root of epsilon naught mu naught. And if you were moving relative to that frame, you measure the same beam of light, you're going to get a slightly different value for the speed of light. Okay? Just like, if somebody shoots a beam of light towards you, but he's in a moving car, if the car is moving towards you, then according to him, the speed of light is c, but according to you, the speed of light seems to be a little bit faster than c because he is also moving towards you. The source is moving towards you, right? That sounds like it makes sense. So there seems to be a preferred frame of reference. And we had that before. We had that in the case of sound. When it comes to speed of sound, there is a preferable reference frame, and that is the frame in which the medium is at rest. Okay, when we say the speed of sound in air at STP is equal to 331 meters per second, we implicitly said basically that this is measured where the air is not moving. Okay, we are relative to the stationary air. If there's a wind, right, then we still use the ground as reference. Of course, the speed of light that we measure will be different because the wind actually carries the sound. Okay, so there's a preferable reference frame, which is the frame in which the air or the medium in general is at rest. Everything else, you're going to get a different value. So if we do the same thing for light, doesn't that tell us that there is a special reference frame for which the medium, so-called medium for light, is at rest? Okay, and then everything else is moving relative to that medium, so the speed of light measured in every other reference frame will be a little different, just like in the case of sound. This medium for light is called ether. Ether. And this thing, ether, is quite strange. Because, sound cannot propagate where there is no particles. Okay? It cannot go through vacuum. That is why we can only see the sun. We can never hear the sun because of the vast vacuum that separates us from the sun. But light permeates through the entire universe. This must imply that this thing, ether, must also permeate through the entire universe. And yet, it doesn't have any mass, doesn't seem to have any mass because it's vacuum, right? There's no smell, no nothing. And yet, there is strangely such a medium that exists for the entire universe. And even though it doesn't have any mass, it seems to be extremely elastic, because the more elastic the medium is, the faster the wave that propagates through that medium, right? Which means it's very strong. So it's extremely strong, and yet it's massless. So that is really weird. Okay, and no matter how weird it is, we still have to conclude that it exists if we believe that there exists this preferable reference frame in which the speed of light is calculated. It's equal to 1 over square root of epsilon naught mu naught. So with that in mind, we can try to find how fast the Earth moves relative to that medium. Remember, that medium permeates through the entire universe, even in vacuum. And you can think of the Earth as moving through that medium at whatever speed, right? And scientists set out to measure how fast the Earth moves through that medium. And the famous experiment in association with that is the so-called Michelson-Morley experiment. It was performed near the end of the 19th century. So let's talk about the Michelson-Morley experiment.